Here it represents a 0, and you can use this mechanism for a fairly efficient way of designing memories. However, these tend to be slower, and these memories are faster. Now there are different types of storage elements. So for example, you can have single input, for example, you can have the D flip-flops, and you can have multiple inputs. So you can have two inputs to a flip-flops. But D flip-flops, I think that is the only example we are going to use, because they're easy to remember, and we can do anything with D flip-flops. Now, since some of you are electrical engineers, you know that the other flip-flops will sometimes lead you to a better design. But let us keep our discussion simple. But actually, I should have said double inputs. To make it more specific. Now there is an aspect of timing. Different flip-flops will respond differently depending on how they are constructed. So some of them are edge triggered. They will respond to a rising edge or a falling edge. So they may respond to a rising edge like this, or sometimes they will respond to a falling edge of the clock. And sometimes they could be pulse type. That means they will respond to the whole pulse. So a flip-flop needs to see the whole pulse before they will respond. So we will not worry too much about that. We will assume that it is edge triggered. Perhaps we will assume that they are rising edge triggered, just to keep our discussion simple. Now, flip-flops, they sample the signal sample the signal at the input, and now flip-flop, they synchronize the transitions. So sampling will be done during a fairly short period of time, perhaps during a rising edge. Now during the time of sampling, whatever is being sampled is required to be stable. So you need to watch for this. When input is sampled, and when the outputs respond. Usually there is some delay. So even in case of a rising edge triggered flip-flop, there's a little bit of delay because of the propagation delays within the flip-flops. Let's look at an example. So let us say here we have a D type of flip-flop. So here is the clock, and here is the D input. Now flip-flops usually will provide you both complemented and uncomplemented outputs. And you can describe the behavior of this flip-flop using a table. So there is current value of output Q. Q is whatever is stored in the flip-flop, and the future value of Q. And for convenience, let's call it Q q sub t and q sub t plus 1. So next value of q, and as you will recall, output of a D flip-flop is going to be same as whatever is at the input, except it needs to wait for an appropriate transition of the clock. So whatever is the value of t here. Okay, let's look at a timing diagram here. So let's have a diagram here. So let's say here is the clock. And here is the D input. D is our data input. And just to make it interesting, let us assume the D input, wherever it is coming from, looks like this. And let us assume that, now this implies, notice this triangle here, this implies that this is a rising edge triggered flip-flop. So this here is rising edge triggered. That means something is going to possibly happen on the rising edge. Now, in case of a rising edge triggered flip-flop, input is sampled on the rising edge, and output will also respond at the rising edge, except that you need to allow for some propagation delay, which is always there. So here is how the output Q will look like. Let's assume that it was 0 at the beginning. And there are not going to be any changes until a rising edge is encountered. So here is a rising edge. And at the rising edge, since it samples a 1, it will respond with the output 1. And here is a propagation delay. So this here is your propagation delay. And then output is not going to change any time until the next rising edge. And on the next rising edge, the flip-flop looks at the input, which is 0. And at this time, it will go down to 0 after some propagation delay. So things are going to be like this. So little propagation delay here, little propagation delay here. And notice that input D went down here, but the flip-flop did not respond because the flip-flop stores a bit of information, and it will store it until the next rising edge of the clock. And notice that during sampling, the inputs must remain stable. If they are not stable, then the flip-flop may get confused. You will not know whether it is going to sample a 0 or a 1. And in some rare cases, there is possibility that the flip-flop may get into some metastable state, which is a state between 0 and 1. And sometimes a flip-flop, once it gets stuck into a metastable state, it may stay there for a few nanoseconds. So, and that is going to confuse the logic that comes after the flip-flop. So there are some mechanisms for doing some design. So probability of such synchronization failure is minimized. But basically, the idea is that during the time when an input is sampled, it should be stable. Now that has an implication on the clock frequency of the circuit, which I will mention about later. Any questions about flip-flops? Okay, now let us come to sequential circuits, which would include flip-flops or other kind of storage elements. And finite state machines. Now this is a mathematical term, so this is a general term, and the sequential circuits are an example of finite state machines, and they're actually a good example of finite state machines. You have other examples of finite state machines. For example, it is very common for the software to be modeled as a finite state machine. And also, when you look at communications protocols, they are sometimes specified using finite state machines. So some of the things here are actually quite general, even though here we are talking about hardware. Now, finite state machines, synchronous sequential circuits, one part of that is some combinational circuit, and this combinational circuit feeds some storage elements. Let's assume that we have a bunch of rising edge triggered flip-flops. Here we have the external inputs. And here we have the outputs. And here we have the inputs to the flip-flops, and here is the current. So here is your state of the finite state machine. So these are the outputs, and outputs of the flip-flops are basically what is stored in those flip-flops. So this is basically the state. And as you know, in a synchronous sequential circuit, the next state is some function of the present state and the next present state and the inputs. I suppose we could call these things collectively as the input. So next state depends on the current state and the input. So remember, these lines, they basically give you the next state. In case of, if there's a flip-flop, then whatever you have here, that is going to be the next state. And next state obviously depends on the input values and the values corresponding to the present state, and also the output. Let's call these lines collectively the output. Also depends on the state and the input. Basically, this is what characterizes finite state machines. Now let's look at an example of a finite state machine. Oh, incidentally, we had a brief introduction of the people in the class. So, can you introduce yourself?
Sure. I'm Havish Khemka. I'm a PhD student